wanted to give a quick demo here about friction. So I got a wood, got a piece of a book here. If I push on it, it's not moving. So there's static friction. If I push harder, there's more static friction because it's pushing back more. If I push really hard, it starts moving. Now, as I said in the previous video, that kinetic friction is normally less than static friction. And so that means that as I push it, it takes more force to get it going, but once it gets going, it's easier to push. Likewise, right now, the static friction is 0 because I'm not pushing on it. If I tilt it a little bit, there's a little bit of static friction because now the normal force is going to be, well, what's going to happen is that there's a little bit of mg sine theta down the incline, therefore there's got to be a little bit of friction. If I tilt it more, there's got to be more static friction. If I tilt it too much, then what happens is that eventually the static friction gets to where it can't hold it. And so that means if I were to find the angle at which this is tilted, so that's tilted at about 25 degrees. So that means that if that's tilted at 25 degrees, in the previous couple videos you saw that for static friction, that means if I were to take the tangent of 25 degrees, that would have told me that the coefficient of static friction there is 0.466. Okay. On the other hand, my calculator is a smoother surface, so as I tilt this, it doesn't necessarily get up to the same angle that it did before, and so now that's going to be 20 degrees. And so that means that the coefficient between the calculator and the board is going to be 0.36. So it depends on the surface. One side's painted, the other side's not, so that's going to give you a different coefficient of friction. It depends on the object here, and then if I were to wear this down the surface, it would also change the coefficient. So there's a variety of different things there that make the coefficient a little bit different. Now the other thing is rolling motion. So if you had like a wheel or something round, so if we have a round object here, then one of the interesting things is that if you look at it, at the point of contact, it's temporarily stationary right there. This is not rolling, that's sliding here. This is not rolling. This is rolling motion. So that means that the point of contact is temporarily stationary. And so that means static friction at work. So if you're stopping your car, then the friction between your tires and the road is greatest if the wheels are moving. If you lock up the brakes and you start skidding, now you have less friction stopping the car, and now you have an increased stopping distance. And so that's why modern cars typically have anti-lock brakes, so that when they sense the wheels stopping rotating, they back off automatically and you go. Older cars that don't have anti-lock brakes, then you would have to actually get off the brake a little bit in order to let the tires roll. Watch race cars, NASCAR, they don't have anti-lock brakes, and so if they go into a skid, then what happens is the driver turns the wheel to get the wheel and gets off the brakes, so the wheels start turning again, and so you turn into the skid, get the wheels turning, and then you can regain control of the vehicle. And so we'll talk more about that later on, but I thought I'd give a brief example right here.